Hi, everybody. So here we are for our next ecology lesson on equilibrium, biodiversity, and biodiversity under attack. Okay, so I'm going to split up this lesson into two parts again, so it's not too overwhelming. About 45 minutes today and 45 minutes tomorrow. All right, so let's begin. Let me share my screen. And all done. Here we go. Okay, so please, like usual, maybe grab someone to discuss some possible answers with, or don't be ashamed to speak out loud, as that is pretty much what I look like I'm doing right now, sitting in my room, okay? All right, so some questions to discuss. If we were to describe a whole biome using select words, okay? So this is the fact that we've done some research on, okay? So certain biomes share characteristics throughout that whole area of land, very similar precipitation rates, very similar climate, okay? Very similar wildlife, terrestrial, aquatic, okay? So how is that possible? How are we able to make a generalized statement about a whole biome? How is it possible for one area to be classifiable based on similar characteristics? Biomes are what? How did this become a possibility? To describe a whole huge area of land over time with similar characteristics. Fact of the matter is, biomes are stable. Okay, that's why we can make assumptions about a whole biome, because it maintains those abiotic and biotic characteristics, the similar types of biotic interactions, similar types of ecosystems, similar types of abiotic factors like light, temperature, precipitation, etc. Okay, so now again, back to the previous lesson. If we're saying that this area is stable, and it's stable over a long period of time, what is that term? Sustainable. Now, there's another word that refers to something being sustainable, okay? When the population size stabilizes, the number of births is equal to the number of deaths, the population is said to be in blank. What is that word? Equilibrium, okay? So all these terms are related. When an area of land is stable, it is also typically sustainable, meaning the population size is in equilibrium, meaning the number of births and number of deaths are fairly similar, okay? So this was the definition that we used to represent equilibrium when we discussed the size of a species population. If I ever say that word, equilibrium, I'm saying that the number of births and number of deaths are approximately equal. Okay, so let's talk about equilibrium, equal values in an ecosystem. So if I'm saying that an ecosystem is experiencing equilibrium, this again is saying that biotic and abiotic features are blank over a long period of time. So, and then an ecosystem that is in equilibrium is also typically said to be blank. So this would be our stable. So an ecosystem that is in equilibrium is stable. And then therefore we can call it sustainable. Okay. Here is where I want you to find a partner. Sorry. I think the section that I wanted either erased. Here we go. Okay, I'll go back to the previous slide after this. Okay, I want you to be specific. Think about the previous chapter. Be specific and discuss which components of an ecosystem is stable, okay? Equal values, before and after. Pause the video. Try to think of parts of the ecosystem that stay the same, okay? All right, so give it a pause. Okay, so welcome back. This question is talking about all of the cycles, okay? Why does the water stay the same before and after? It's because it never really disappears. Ultimately, it goes back to that law of conservation of mass as well. Since matter cannot be created or destroyed, it is always technically balanced. It's just kind of moving through its different forms or cycling through different forms. So, number one. Let's write about matter. Matter is stable in ecosystems. Water quantities, nitrogen cycles, carbon will cycle, and they will remain in relatively stable quantities. So, I mean, yes, this kind of goes against that understanding that if matter is always stable, how are some ecosystems unsustainable if the matter is stable? Okay. Well, now here's the thing. I want you to imagine, actually, a simple example is a front lawn, okay? Typically, the grass that they use has originated not from a drier climate, but from a wetter climate. So that's why a lot of people need to water their grass to add extra precipitation, more so than what Ontario can actually provide. Otherwise, the grass will die in the summer. Okay, so different grasses are adapted to different quantities of water. But if you put a type of plant that's adapted, let's say a cactus, to very minimal rainfall, and then you put it into a rainforest, okay, now that will cause it to die, okay, because it needs less water to cycle, okay? It creates an imbalance of the proportions that it has adapted to, okay? The most simple one about how matter kind of replenishes itself and remains stable and literally remains balanced. Think back, what equations did we physically balance to make sure the quantities on the left were the same as the quantities on the right? And those biotic equations were photosynthesis and cellular respiration. The whole process that creates life and allows life to continue is a balanced process. Same amount of reactants as the amount of products, all again back down to the law of conservation of mass. And then as a result of all of this, that is how we create stable populations. When our birth rate equals our death rate, when the predator-prey relationship is balanced, when the competition is balanced as well. So populations will also remain relatively stable when they are in a balanced food web. So it's just amazing how it all starts from the chemicals, because the chemicals are always balanced, because the photosynthesis and the cellular respiration has the same reactants as products. That thing that gets brought into the food web, okay, then exists in the food web and now is cycled around. So you still don't lose it because it cycles up into the atmosphere, comes back down, okay? And then even that, when you put it into a real life living organism, it still remains balanced because everything in an ecosystem will balance out. The population, predator, prey will start to balance itself out in a way so that it is stable and sustainable over time. It's really quite a beautiful thing. Okay, so if an area is in equilibrium for a long time, what is the word for what species will do? So you are an organism living in an ecosystem or in a biome. It's in equilibrium for so long that species will blank to the biotic and abiotic factors that are in that area. The best word for this would be the species will adapt or evolve, okay, to those conditions. All right, so now let's think of a list of natural factors, okay? So non-human caused things, okay, or actions that can kind of disproportionately skew a food web, okay? So what can cause short-term changes to an ecosystem? Okay, so I want you to pause the lesson, think of a bunch of natural, non-man-made factors that can cause a short-term change to an ecosystem. So put everything off balance. Pause, and I will come back. Okay, So what I'm doing is I'm backing up to show you. Here we go. Anytime there is a volcanic eruption, that is a natural factor that is kind of destroying that whole ecosystem. And today I will teach you about how does that ecosystem eventually come back. There is a word for that, when the ecosystem can rebuild itself over time. Try to think of what that word might be. In the same line of volcanic eruptions are things like earthquakes, hurricanes, tornadoes, okay? Tsunamis, any of these things. Forest fires are also naturally caused a lot of the time. And another natural factor, although humans have, what's the best word for this? Exacerbated the problem, which means made it worse, okay? And also probably increased the rate of disease because of our huge quantities of humans. But disease is typically a natural thing. Don't write food chain gizmo. I will just show you the food chain gizmo. Okay, so now let's take a look at this gizmo together. So here we go. So let's kind of read this out here. This simulation allows you to explore a food chain. In this particular chain, the rabbit eats grass, the snakes eat rabbits, and the hawks eat snakes. All right, so now just take a look. What I'm going to do is I am simply going to press play. Play will represent that the ecosystem is growing, existing, that time is beginning, okay? So just watch as I press play and quickly look at the numbers. Notice the producers are changing, but still 27,000, 27,000. The rabbits stabilizing around 25,000, 2,500. Snakes barely changing, hawks barely changing, okay? And now notice, after about 19 months, the numbers are barely even moving. All right, so let's look at it again with, I think, let me just, this one's pretty good. Let's watch it on a bar graph. Stabilized, let's watch the graph. Stabilized, table, stabilized, okay? All right. Now let's tweak it. Let's make our grass diseased, okay? So you're going to see a lot of changes happening, but then it should stabilize at a new norm. So let's play. Okay, ready? We've diseased our grass. So watch the green line for grass. Watch. Everything drops with it and then balances at a new norm around this diseased grass. Okay, so keep watching. Yeah. Okay. Now, let's bring everything back. Let's disease our rabbits. Let's see what happens. So watch the yellowish green line. Ready? Diseased your rabbits. Look at that grass growing, growing, growing. But then things are going to start to normalize. Again, they're going to essentially plateau. Okay. All right. Let's disease our snakes. Now let's watch the purple line plummet. Hawks should be going down with it, which they are. Rabbit numbers going up, 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 causing grass to go down, but then again plateaus over time, stabilizes at a new norm. And last one, let's make our hawks diseased and watch. Drop your hawks. Everything else should be doing a little bit better. But then again, there are not unlimited resources. You cannot just everything increase, 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 okay? So then it will stop increasing and stabilize. Yeah, ultimately diseasing them is the same as removing certain number of snakes, et cetera, okay? So that is our food chain gizmo. Okay, and let's continue. Okay, so now let's talk about the succession. Okay, so this is the term that I was asking you before. When you have something like a forest fire or a volcanic eruption, over time, somehow, it is possible, even on bare rock, for an ecosystem to reestablish itself. This ability to reestablish yourself is called succession. So let's write that. Okay, succession. The process of re-establishing an ecosystem, so an ecosystem community following a disturbance. So typically, succession is possible after natural factors, volcanoes, forest fires, earthquakes, hurricanes, whatever. But don't forget, in the last lesson or a couple of lessons before, we talked about man-made changes. Whether it's clear cutting forests and plowing, creating roads on them, creating new whole urban centers, farming, mining, okay, any kind of urbanization. The issue is this: man-made changes can be even more extreme than a volcanic eruption. As you know, if you're paving a road, my goodness, the amount of years it'll take for any kind of roots to try to grow out of that soil, it seems to be nearly impossible, because if there's no photosynthesis, no light getting to the soil underneath, how can any bacteria survive? How can any bacteria bring nitrogen into the soil? How can any plants grow out under that concrete, right? So the theme is this: succession is not possible if the change is irreversible, and typically these are man-made changes. Of course, I'm sure a lot of you are going to argue, okay, well, wait 1,000 years. Sure, probably in 1,000 years, succession can happen. But succession over thousands of years is not really the definition that we are referring to when we are talking about ecological balance and how long an ecosystem can take to reestablish itself. So let me show you an example. Okay, so in 1980, oh my goodness, how many years ago now is that? 40 years ago, Mount St. Helen erupted. Okay, so it's just a mountain in Washington. It wiped out all the life on the mountain. Now, life has reestablished itself. So I'm going to show you a picture of Mount St. Helen before it erupted. Try to analyze what level of plant growth you see. I'm going to show you a picture of Mount St. Helen after it erupted and Mount St. Helen today. Okay, what plant growth can you see today, 40 years later, after the whole ecosystem got wiped out? Here we go. So the back picture, it's really blurry. I'm sure you can find some other ones. But ultimately, you can see evergreen pine trees growing, right? So hardwood trees are growing. Essentially, that's a whole forest at the base of a mountain, just like anywhere else. You'd find a full forest. After the volcanic eruption is literally nothing, okay? Bare rock. This is what we call primary succession. When a disturbance wipes out so much of the ecosystem that essentially it is starting from scratch, okay? There is a difference between a volcano and a forest fire. One of them is primary succession, like a volcano, bare rock. One of them is called secondary succession, starting with a little bit of living organisms around still. And this is Mount St. Helen 40 years later, okay? These trees that you can see poking into the distance, they barely count because they have got to be like, I don't know, 10 kilometers away even from the apex, okay? So what you're trying to analyze are the plants that are closer to the volcano, and I will show you another picture later. So this is an example of primary succession. You have reestablished an ecosystem, but it's on bare rock or soil. There's no life following a hardcore disturbance that destroyed the whole community. So this Mount Helen example. So by comparison, secondary succession is when you reestablish an ecosystem and following a disturbance, but that disturbance did not destroy the whole community. So after pollution, possible mining, forest fire, that would be secondary succession. Okay, so pause it if you need more time. Grab a partner and please discuss. What do you think the steps are if we are going to reestablish an ecosystem? What comes first? What kind of plants do you start to see first? Do you see animals before plants? Do you see plants before animals? What kind of plants would you see? What kind of animals would you see? Okay, so pause and come up with a list. I think we have five general categorizations that you can think of. Okay, so these types of things first, and then these things will start to grow, and then these things will come in, and then these things will grow. Okay, so pause. Okay, here we go. The first thing that we are going to have growing after for primary succession, growth on bare rock, are the types of producers that can grow on bare rock. Lichen, moss, fungi, okay? Fungi is a tricky one. I actually wouldn't even call it a producer, okay? So these are called perennial plants, long-living plants. So perennial plants and herbs, your moss, your lichen, your fungi. Now, what they do, and the reason they can survive, is lichen have the ability to take nitrogen right out of the air, okay? So they don't even need soil really for their nutrients. They can get it out of the atmosphere. And as they do this, same with fungi, what they do is they can release essentially kind of like digestive juices that can start to break apart the rock. And as these things start to grow on the rock can start to decay and break down into essentially the soil that it will form. So these plants are helpful because what they do is they start to break down that rock into soil. So the first thing you'll start to see on that bare rock are your lichen, moss, fungi. And they are going to start to break down that rock. And remember how we said in a previous lesson, the pH level of soil is based on the rock within which it came from? This is step one, right? Bringing that rock into its soil. Okay, so now let's say we have a thin little layer of soil forming. What kind of plants will you start to see now? And as a result, are you going to start to see any animals with regards to those plants? What is the next level of plant? So next, what we have are your grasses, flowering plants, small grasses. Yes, at this stage, you might have some insects coming in, but in terms of mammals, no, there's not enough here for a safe habitat for many of them. After that, you'll get some small shrubs. At this point, when you have some shrubs, this is now able to serve not only as food, but as an actual habitat location. Remember, niche, what it eats it, and how it behaves. So you can't just forget about that third component to a niche. You do need to look at where it would live. And now we can start to get small animals such as squirrels. And now that you have soil, now that you have plants which have roots, which have the ability to do mycorrhizae, now that you have animals possibly dying on that soil or I guess urinating or I guess pooing, sorry, what's the fancy word for that? Removing feces, I don't know, onto that soil, it can undergo its process of ammonification, NH3 to NH4+. Then it can use nitrifying bacteria to go from NO2 to NO3. And now we have nitrate to provide reestablished nitrogen in the soil. Okay? So lichen don't need nitrogen in the soil. They can get it directly from the atmosphere. So that is how they could survive. But after we start to break it down, we do need to get the bacteria back into the soil to do nitrogen fixation. Okay? And then the benefit of having organisms living on that soil is they will release animal droppings, that is the word, and also die on that soil, and their dead, decaying bodies will reestablish nitrogen to that ecosystem. Okay? Next, we have our softwood trees, and then after that, we will have our hardwood trees. Softwood trees are our pines. Again, now you can have larger species, having that as a source of habitat, larger birds or birds at all. And then come the hardwood trees, your maple, your beech. And again, larger animals will move into this ecosystem until it becomes sustainable, or sorry, until it becomes stable again. Stable, sustainable, equilibrium, all of those words are fine. Okay, pause and answer this question. How long do you think this process takes from bare rock to equilibrium hardwood trees? Guess. It takes more than 150 years, believe it or not, okay? So you might think, okay, Mount St. Helen, 40 years ago, okay, get over it. I'm sure we have a forest there by now. No, I will show you a picture, okay? It takes a while to get to that level of hardwood and softwood trees. Okay, so on this diagram, you have a visual depiction of what's going on. I want you to label it as best as you can, showing where would the lichens and the moss be, where would the perennial plants be, where would the shrubs be, etc. Okay, so pause it and I will show you a fairly accurate depiction in the next slide. Okay, so here you go. We start with our bare rock. So that is what the first one represents, okay? So after the disturbance, we have our bare rock. It's very hard to see on your lesson, but take a look here. This is an image of what lichens look like. If you're interested, I would do more research. I definitely think we talk about these more in grade 11, okay? Then you have your grasses. So plants, lichen, grasses and perennials. For me, I just lump those together, the grasses. And again, now you have shrubs and pines. And then the next category are the hardwood trees like oak. But notice that x-axis there, the descriptor, hundreds of years. Okay, so pause. I'm going to show you an image of Mount Helen as well. And we have 5 categories, 1, 2, 3, 4, 5. I want you to decide which one is it at. Perennial plants, grasses, shrubs, softwood, or hardwood trees. So here's a picture 40 years later. Discuss with a partner, which stage do you think it's at? 1, 2, 3, 4, or 5. So in my opinion, if you take a look, I don't really see any shrubs yet. Maybe a couple in the back there, but it's actually number 2. We've got your flowering plants, you have your grasses, but there's maybe 1 or 2 shrubs starting to form that might come up in the next 10 years or so, okay? But as of now, we're somewhere between step 2 and step 3. All right. So this is the coolest thing that I found. Sometimes the first plant that will be found is called a prairie lupine. So that's random, right? But it has the skill of taking nitrogen straight from the air, just like a lichen, okay? So these are wildflowers, and that can bring that first set of insects and herbivores in. So this thing about catching blowing leaves, it can kind of create a little bit more of a system to prevent erosion, okay? Anything that can be captured to protect the ground can prevent the soil from eroding away, okay? So it's actually quite interesting that this is the first real kind of flowering plant to emerge, and it's because it can get nitrogen from the air. Remember, see how it all begins with needing to reestablish nitrogen in the soil. Okay, so we're going to spend a few slides talking about biodiversity, and then I will continue in your next lesson, okay? So what is biodiversity? How would you define it? Biodiversity. Biodiversity. So this is the variety of different species. How many different species can you find in an ecosystem? That is biodiversity. Okay. So these stats that I'm going to show you, it's just for interest's sake. It starts to get a little bit confusing when you start to talk about undiscovered species, because I know everyone's always like, well, if we haven't discovered it, how do we know they are there? It is an educated guess based on different types of extrapolation, okay? So what we have found to the areas we haven't started searching yet. Okay, so there are theoretical numbers the scientists have put forth to theorize how many, sorry, what is the word? Undiscovered species they think are left in the world. So as of now, 4 million, oh, I should have gotten you to guess. 4 million species have been discovered. How many do you think are left undiscovered, according to their theories? Unless I already told you. How many do you think have been undiscovered so far? If there's 4 million discovered, scientists theorize that the total number of species on Earth lands somewhere around 9 million, meaning there are 5 million left undiscovered. All right, so there are some categories of organisms that scientists are pretty sure that they have found almost all of, if not all of. There are categories of species that scientists think they have not even scratched the surface of classifying and identifying yet. So I want you to come up with a list. Write down which organisms you think we have found almost all of, which ones do you think we found most of, which ones do you think we have found the least of. Okay, there are 5 different categories here. Try to give it a guess and please pause and discuss. Okay. So the biggest category, I think hopefully you guessed this, are our mammals and our birds because they are big enough for us to see fairly easily. So, I mean, this estimate of 10, it's kind of random. Ultimately, they think that they've discovered all of them, okay? But there might be 1 or 2 here and there deep in the Amazon rainforest, okay? Then they think that they have discovered most of fish, reptiles, amphibians. In that category, they theorize that there's about 20,000 undiscovered. Then they're thinking that we know a little bit less about the number of plants that are out there. Approximately 80,000 plants left undiscovered. So in grade 11, you're going to learn about taxonomy, the process of classifying living organisms and trying to categorize them into different species. And certain organisms, such as plants, they are really hard to tell the difference between different species. A lot of times they can look very, very similar to one another. And that is the hardest part, that species that look very similar, if not identical, are different species, and it's hard to identify. Then we start to go into our aquatic creatures, because again, the oceans are a vast area which large areas have been unable to discover the depths of the oceans. Snails, sponges, any of those different types of organisms. They're arguing that they're up to 1 million. Okay, what is our last one? There is essentially 4 million organisms left, okay? A little less than 4 according to my math on this table. What is that big category that scientists are acknowledging that they have not found a huge quantity of them and that there are a huge amount of them still out there on the earth, but we just can't find them? Hint, hint, because a lot of times we can barely even see them or catch them. Which ones are these? Your insects. 4 million undiscovered. So this data, I didn't just make it up. I found it from this table that looked at the different undiscovered theoretical quantities of organisms. So you've got your approximate 20,000 here of reptiles, fish, amphibians, your insects of at 4 million up there, and I added up your plants quantity to about 80 million. It's actually probably, yeah, your plants quantity to about 80,000. As I'm doing the math quickly here, it looks like 90,000. So there's probably an inaccuracy in the data there. Okay, so just so you know, you're looking at this list. Arachnid, what is that? So think about it. If I say the word arachnid, what kind of animal is that? So your arachnids are your spiders, your mites, your scorpions. If I say a mollusk, what is that? That is your shellfish, snail, squid. Crustaceans. Those are crabs, shrimp, lobsters. Echinoderms. So again, you'll learn all about these in grade 11. Echinoderms, starfish, sea urchins, sea cucumbers. And when I say the category of other, those are things like worms, centipedes, sponges, jellyfish. Okay? All right. So now we're going to play a little game. I am going to show you a list of species that have been discovered within the past few years. Okay, I think it's now 3 years ago they were discovered. Approximately 18,000 new plants and animals are discovered each year. So scientists are discovering them at a rapid rate. That is another fact that they can extrapolate. If they're discovering 18,000 new plant or species every year, that means there is a whole great deal of them left out there if they're able to find so many. Okay. Over the past few years, they found 70 new reptile cases, 400 new fish. And every year, the Environmental and Forestry College compiles a list of their favorite species, just kind of for fun and for interest. Okay, so let's see what they found. So this part I usually do in class. I do it as a trivia style. I'm just pausing because I'm thinking maybe I'll do it for our next trivia game. Okay, well, I guess so this is good practice for the next trivia, if it's possible. I'll probably get you guys to spell these correctly. But this game, if you have company, is to say it as quickly as possible and as accurately as possible. Ready? All right. So this first one, I'm not going to show you the name of yet. What do you think it was named after? So take a look at it. This is a 2 millimeter, so it's tiny, a 2 millimeter long spider. What do you think they named it after? What does it look like? All right, I'll give you a hint. It looks like something you might see in Harry Potter. All right, so they named it after Gryffindor House for the sorting hat. I'm hoping one or two of you got that guess, sorting hat. So ready to race the name. 1, 2, 3. Okay, Riovixia Gryffindori. Okay, so it was named after the sorting hat, okay, in Hogwarts. Okay, next one. Take a look at this guy. That is a knuckle that it is found on, right? On the person's knuckle, it's sitting, just to show you how big this organism is. The reason they haven't found it is it just blends so perfectly with the type of plants that they tend to habitate, okay, on. So they have not been able to find it, even though it's so big. It just blends so perfectly to the plants that it feeds on. Okay, here we go. 1, 2, 3, the name. Eulophyllum kirki. All right, Eulophyllum kirki. Okay, next one. So this is a perfect example. It's like, okay, yeah, Ms. Romanovsky, it's a rat, calm down. Again, there are different species. This rat cannot mate with other rats, and therefore it's its own species. And actually, you know how we talk about what it eats it, and how it behaves? It behaves so differently from all the other rats. That's why it's actually gotten its own category, okay? So it's an omnivorous rat, and it just behaves so differently from the other rats around it. Okay, so the name, ready? Gracilimus radix. All right, one last one. This one's really cool. Okay, it's named after something. Okay, so if any of you guys guessed a transformer, that is, in my opinion, the best guess. That is not what they named it after. Okay. So I'm just, now that I'm analyzing and just sitting here, I'm realizing that I've always thought that it looked like a transformer standing on its legs and facing us forward. But no, you analyze it, the thing to the left is its head and it's facing the left. Okay. So they name it after something in the Game of Thrones. The front of the head, does it look like anything from the Game of Thrones? If you have ever watched that show, which I have not. Okay, ready? And its name is Fetal Dragon. Okay, and it was apparently named after the spiky armor from the dragon in the Game of Thrones. So I tried really hard to find it. And look at the sizing, right? 1 millimeter. So this guy's about 2 to 3 millimeters in size, quite small. So I tried to find an image of the dragon from the Game of Thrones, and this is what I found. So I guess they think the spiky armor looks similar. Okay, and let's finish this off. How do we measure biodiversity? If biodiversity looks at the number of different species, okay, found in an ecosystem, how do you measure it? Well, it's as simple as you count the number of different species in that habitat, okay? So if we're looking at the number of different species, well, to measure is you count the number of different species in that ecosystem. And then you can compare it to other ecosystems around. This measurement, if an area is very biodiverse, it is said to have a great deal of blank. And you would never have heard of this terminology, but any ecosystem that is said to have a large number of different species is said to possess species richness. So that's essentially another term for the number of species in a habitat or ecosystem. Okay, so now let's take a look at this map here below and take a look at it and think about which part of this world do you think would have the greatest biodiversity? Think back to the biomes that we studied. Which biome had the most species richness? So the best answer here is your tropical rainforests. Okay, so I have a diagram here to show you the major rainforests where they be found in the world, and notice that they are all around the equator. Okay, so the tropical rainforests have the highest biodiversity compared to all the ecosystems on Earth. Okay, so all of them, this is where you'll find the highest amount of biodiversity. So let's take a look at the Amazon rainforest, okay? In Ontario, we have one species of hummingbird. I'm sure it has a very fancy scientific name, but we just call it, yeah, it's our hummingbird. Sure, we've got the one. But in the Amazon rainforest, how many species of hummingbird do you think there are? So give a guess. So in Ontario, we have one. Amazon, they have 200. It really just blows your mind when you start to think of it like that. Okay, so let's finish it off. Let's now take a look at, we've discussed this before, how can you change an abiotic factor and cause it to increase biodiversity? So come up with some predictable trends with a partner. I want you to write, I've actually kind of restricted it to look like, sorry, I restricted it on your lesson to look like this. If you increase blank, you increase biodiversity. If you increase blank, you cause an increase in biodiversity. Okay, so pause it, Look at those trends with a partner and try to figure out what those words should be. By increasing this, you get more biodiversity. By increasing that, you get more biodiversity. Okay, so pause and I'll come back in a second. Okay, so if you increase your precipitation or rain or water availability, you increase biodiversity, hence the rainforest. If you increase your temperature, you increase biodiversity, okay? If you increase or improve soil quality, or if you increase the available soil, you increase biodiversity. And of course, if you increase the amount of light, that is the source of everything, okay, then you increase biodiversity. Okay, so all of these, okay, if you increase them, they cause an increase in biodiversity as well. Okay, so let's fill that in. An increase in temperature, an increase in precipitation, an increase in the soil quality, or an improvement, okay, is a better term for that. An increase in water availability, and an increase in amount of light. So we're going to finish off this lesson just by doing a direct comparison. So let's take a look at the tundra, and let's take a look at an image of the tropical rainforest, okay? All right. I think it is very clear here that one has lower biodiversity and that the other one has a very high biodiversity. But let's bring it back to abiotic factors. So for the tundra, describe its soil quality and precipitation, possible light or temperature. And for the rainforest, describe its precipitation, light, soil, etc. Okay, quick pause, and I will take it up in a second. So if you go back to the lesson, your self-learning that hopefully you guys are all working on, the tundra, temperature, cold. Soil quality, poor. Precipitation, low. Okay? Cold, poor soil quality, low precipitation. Yes, you might argue, oh, but miss, there's so much sun. Yeah, it can be sunny, but if the soil sucks and it's cold that different organisms can't survive there, it's not going to help. And if there's no rain to water those plants, that sun is useless. Okay? Tropical rainforest. Temperature, warm. Precipitation, high. Soil quality, high. Okay. All right. And that is it for today. There's no homework on this. Just tomorrow or the day after, I will give you guys the rest of this lesson, which starts by looking at the benefits of biodiversity. All right, that's it for me. Have a great day, everybody.